Today we're going to look at integration by parts. With differentiation, we know that there's two extremely powerful rules, the chain rule and the product rule. And we've already seen on our video on substitution that we can reverse the chain rule and use it to solve some integration problems. What would be nice is if we could reverse the product rule as well and use it to solve some integration problems. And in fact, we can. That's what this whole video is about. So let's refresh the product rule. The product rule says that d dx of uv, a product of two functions u and v, is equal to v to u dx plus u to v dx. And what we want to do is now take the integral of both sides. Now we can use two things to help us out here. On that left-hand side, I can use the fundamental theorem of calculus to realize that it's just inverse operations, an integral and a derivative of the same variable. I can just cancel it down and get uv. And on the right-hand side, the great thing about integration is it behaves really nicely with addition. So I can break that integral of a sum into a sum of integrals. Another great thing about integrals is, and we're not going to prove this in any way, you'll just have to wait till university to see this in operation, but that d dx and the dx, they act just like normal fractions. They cancel each other out. What I'm going to do now is I'm going to keep that integral of u to v by itself, isolated, and I'm going to pull the other integral over the other side. That now is the new tool to put in our toolbox. This is what's going to help us with integration by parts. What we're saying is we've got the integral of a product, but it's not like the product rule where we had u and v. Now we're saying we've got an integral of a product, but the product is made up of u and v, the derivative of this function v. And we're saying, okay, we can't solve that integral, but maybe this new rule is going to help us out. If I can work out what u and v are themselves, then I can say that the integral of u to v is equal to uv minus the integral of v to u. And hopefully that second integral is something I can solve. Either it's straight away a standard integral on my reference sheet, or it is something I can manipulate with partial fractions or substitution or something like that to solve that integral. So let's solve a simple problem. Let's try and do the integral of x cos x dx. As is, that is a product, x and cos x, and I can't solve this at the moment. It's not one of my standard integrals. Substitution's not going to help me here. So really integration by parts is the logical choice. So what I'm going to do is I'm going to set u equal to x and v equal to cos x. So that's the derivative of this function v that we want. Okay, so take the derivative of u and we get du. Du is just 1. Integrate dv cos x and we get sine x, so v is sine x. So our rule now says that I've got the integral of u to v, which I can't solve, but I know that's equal to u times v, which is x sine x, and then I need to subtract off the integral of 1 times sine x dx, which is just the integral of sine x dx. And I can solve that one. That's perfectly easy. It's negative cos x. So now I know I've got my answer. My answer to the integral is x sine x plus cos x plus a constant. So this rule is really powerful. Now, the thing about products is they're commutative. It doesn't matter if I do a times b or b times a. So in this case, it doesn't matter which of the two functions I choose to be u and which one I choose to be dv. The rule should still work quite happily. Unfortunately, that's not always the case. We chose u and dv very carefully there so that the problem collapsed, and I got that second integral that was something I could solve, and that's what I wanted. Let's switch them around on this simple example and let's see what happens. So this time let's let u equal cos x and dv equal x. So that means if u is cos x, then the derivative to u is negative sine x, and the integral of x is a half x squared. So that second integral, we won't worry about the rest of it, but that second integral is going to become the integral of a half x squared sine x dx. There's going to be a negative in there somewhere, but that, again, that'll come out in the problem. That's fine. What we want to see is that integral actually got worse. It got worse than the original integral. We can't solve x cos x, and now we're trying to solve x squared sine x. That's even worse. So you need to be careful, even though it doesn't matter which way around. In theory, you choose u and v. In practice, it often does. One way will work quite nicely, and the other way will just make the problem worse. All right, so another simple example. Let's find the integral of x e to the x dx. Again, here we're going to let u equal x, and therefore du is 1. And dv we're going to say is e to the x, which means v is e to the x. It's nice and easy. That's a nice easy integral. So the answer is x e to the x minus e to the x plus a constant. Again, a nice simple problem to solve with integration by parts. So you've seen two examples now where there was a polynomial involved, an x, and often that's what we let u equal, because then when we take the derivative, it reduces the degree, it simplifies the degree of that polynomial, and hopefully makes the other integral easier to solve. Okay, here's a more complicated example. We're going to have to use integration by parts twice. So we're going to find the integral of x squared e to the minus x dx, and we're going to let that run between 0 and 1. So just like before, let's let u equal the polynomial x squared, therefore its derivative is 2x. dv is going to be e to the minus x, and therefore v is minus e to the negative x. So therefore our integral becomes negative x squared e to the minus x, which is multiplying u and v. But because this is a definite integral, we didn't have to do this in the previous two. We actually have to evaluate that at the limits 0 and 1. That's the consequence of the fundamental theorem of calculus there in play. And then we've got the addition of that integral 2x e to the minus x dx, again running between 0 and 1. So that integral that's left there at the moment, again, that's something that's still not solvable. So I said at the beginning that integration by parts is hopefully going to give us an integral that we can solve. Either it's straight away, it is a standard integral, or it is something that we can further manipulate and simplify into a standard integral and solve. So at the moment, it's not a standard integral, but it is simpler than the original problem. In fact, it's pretty much the previous example, except there's an e to the minus x instead of an e to the x. So we're just going to employ integration by parts again on that second piece. So now let's let u equal 2x, and therefore du is 2. And again, we'll let dv equal e to the minus x, and therefore v is minus e to the minus x. And let's run through integration by parts on that again, as you can see. And the problem collapses down now into something we can solve. So sometimes you're going to have to use integration by parts more than once to solve the problem. But the key deciding factor, the thing that should be making you think you're on the right track, is that integral, that second integral that we end up with, is getting simpler. And it isn't just getting more complicated, or it isn't kind of equivalent in difficulty. Okay, so here's another example. The integral of x log x, or let's say ln x dx. Now I said often we choose u to be the u, the thing that we're going to differentiate, make simpler. But let's try that here. If I set u equal to x, then du is 1, dv is log x, I don't know what the integral of log x is. So I can't even start integration by parts if I take this route. So there are exceptions to choosing the polynomial as u. As long as the other thing can be integrated, then it's fine. But in this case, we can't do that. So we've got no choice but to try the other way around. We're going to set u equal to log x. So if I set u equal to log x, then du is 1 on x. And dv, we said that was x, therefore v is a half x squared. And now, if we plug that into our formula for integration by parts, you can see that second integral, the x's start cancelling out all over the place, and it becomes a problem that's really easy to solve. So the exceptions are sometimes there. You've just got to be careful. Often you'll choose the polynomial to be u, but just make sure that dv can actually be integrated. And here's an awesome integral. And this is a tool that we can use all the time. It's really powerful. It doesn't look like a product at first. So we're going to do the integral of the inverse sine x between 0 and a half. That doesn't look like a product. It's just got one function in it. But that's where we say, okay, well, what if we said this was 1 times inverse sine x? What happens then? So again, if we choose 1 and inverse sine x, I can't let u equal 1 because I can't integrate sine inverse x. So I can't choose that to be dv, that has to be u. Thankfully, I can differentiate inverse sine x. So let's let u equal sine inverse x. Therefore, du is 1 over the square root of 1 minus x squared. dv is 1, and therefore v is x. And then I get, plugging into my formula, I get this result right here. And then I can use substitution on that second integral there to simplify the problem. So there we go, integration by parts. You've seen a few different examples. It's a really powerful tool. It's an awesome tool. And you've seen it can sometimes solve problems that aren't even technically products unless we consider the function times one. So a magnificent tool.